Hi, we're group one with machine learning fall 2021. I'm Cailean. You'll see on your screen Landon and Isaac, and we're going to be presenting on the bike share data.
All right, so for our exploratory data analysis, we needed to come up with some questions, and so we went back to the beginning just to get some context on this data. It's comes from Washington, D.C., across the years 2011 and 2012, and it spans every hour for almost exactly 2 years. Every row in the data is 1 hour. And we have descriptions of our variables. A lot of it is categorical and encoded as numbers. And then we have lots of information about the time and what kind of a day it is, whether it's a weekday or a holiday, and how bad the weather was that day, and temperature, humidity, wind speed for that day, as well as the total number of rental bikes that were used in that hour. So to start with, I'm sure you're familiar with the data. So it's relatively clean. Temperature, humidity, wind speed are standardized already. And we just got some plots just to explore, start to try and visualize and find some questions here. So from the pair plots, these seemed to be the most informative, simply because they weren't all integers. So we found that hour and count, as well as temperature and count, had the most well-defined shapes to them. With they both kind of have a bell hump around on the right side. As well as we can see, wind speed and count are slightly right skewed. As for correlation between variables, we started with all of them, of course, and so we can see the bright spots and the dark spots that were most important, such as humidity and wind speed, temperature and count, weather situation and humidity. And so some of the most interesting ones were here, though, with count, temperature, hour, year, and season. Now for some more favorite plots, though. So we can see that the number of bike rentals has a definite pattern throughout the week if we plot by weekday, and throughout the year also with the months. It goes up during the summer and the fall, and throughout the week, Thursdays and Fridays are really popular for renting bikes, apparently. And then just to find out more about bike rentals, we compared the 2011 and 2012. So there were definitely a lot more bike rentals in 2012 on average and throughout the year. And we also took an interest in humidity and weather. So as weather severity increases from clear all the way up to heavy or severe, humidity has a much narrower range and is much higher on average. Of course, we should also note that there were only 3 observations in the entire data set that had any heavy weather in it anyway. But that will be important later. So bike sharing, according to the weather, was much more popular in the clear hours, of course. And just to visualize bike rentals across the entire data set, we have this last chart here. And so our main takeaways from this were that we were most interested in weather situation and bike rentals. And so we came up with a classification question to kind of see if we could reverse engineer and predict what the weather was like based on how many cars were being rented or bikes were being rented. And to for a regression question, to see what models perform the best, can predict, count the best, and to see specifically which features were most important to predicting those. And we did this project thinking more about the exercise than the application. So we use all of the data to classify and to regress, aside from the date. However, we know that in real life application, if we had humidity and temperature and wind speed, we would probably know the weather situation already anyway. So while our models are somewhat unrealistic, we did learn a lot from this project. And so we will go ahead and share with you results from our classification and our regression exercises, and then wrap it up at the end.
Okay, so for classification, we imported everything we needed, and then we looked to see how often fair weather occurred within the model, and we got 65%. So 65% was the accuracy to beat going into our classification models. You'll see here that we started off with trees and worked our way down through all the different models. You'll see Cailean, SVC, logistic regression, etc. We split the data in 70% and 30%, and then we consolidated the results. As you'll see on the screen, you'll see that for the classification rankings, our top 3 algorithms were random forest, XGBoost, and gradient boosting. This was super interesting. You'll see that for all 3 of those models, the accuracy was higher than the 65%. So the no-skill model will also see pretty good F1 scores, starting with 68%, 73-ish%, and 76%, all doing a really good job. To further our understanding of what was going on here, we looked at feature importance for the top models. We'll see here, we are very pleased to see this. So our top model, Random Forest, did have count in the top couple features. You'll see here it had humidity, count, temperature, and hour. For some of the other models, like we'll see here for XGBoost, count was towards the bottom and unfortunately didn't play a large part in its results, but we'll see that in gradient boosting, count is somewhere in the middle. So some conclusions for the classification. Our results were pleasing to us. We did learn a lot about feature importance and how the models varied. Unfortunately, we cannot say for sure that bike rentals are have any more predictive power than some of the other variables in regards to weather severity. But overall, we were interested and satisfied with the results.
Yes, so with the regression, the same situation, we decided to split the data into a 70-30 split. Again, if you'd like to see the implementation, we basically just trained the models and then again compared the RMSE across the models. You can see a little more itemized there. But with our final results, we actually found the top 4 to be similar to the top 4 for classification, but they're slightly different, which we found interesting. For example, here XGBoost was the best performer with an RMSE of 40, with Random Forest close behind, and then Cailean and Decision Trees being essentially a tie for 3rd. So to further our question, we kind of expected these tree-based models might be best. So we wanted to look into the feature importance, like what our question was saying. And for the top model XGBoost, we actually found that not being a business day was one of its top used features for predicting how many would be used. And other than that, hour, year, and temperature were pretty consistent across second and third place as well. And you can see hour, temperature, year, and not business day being kind of, again, the top 4 importances. So we found this interesting because obviously temperature is kind of dealing with weather, but humidity was something that we kind of thought would maybe be important as well, and or maybe wind speed. Sorry, not for the weather, that was classification, but for regression, we just found it interesting that the time was very sensitive as well to how many people would wear the bikes. And like we saw from our EDA, the year, especially being 2012, had a lot more people renting bikes than the previous year. So that was also a good predictor. So that being said, if this model were to be used in practice, and if we were to give this to Capital Bike Share for them to use, it would be important to know that there is an error from what those predictions are, and any use of this should be kind of given as a more generalization, and that more work should be done if they're going to use it to make thresholds of when they should buy more bikes. They should build in and maybe run some analysis on what would be a good threshold, as well as knowing that this isn't linear data. It's not necessarily going to be normally distributed, so they can't necessarily rely on the standard deviation being roughly 40 bike rentals in an hour for what their analysis is. But we still found it to be very interesting, and that they were able to predict, as well as they were, how many bikes would be rented out in a day.
All right, so to wrap up both our project as a whole, we did learn a lot about classification and regression. We would have liked more time to cross-validate and tune the parameters of these models. For instance, none of the classification models ever predicted heavy weather because there were only 3 data points in our set. So we'd like to maybe try rebalancing the data. We'd like to use polynomial features with logistic regression, regularization with logistic regression, and do a lot more with that, as well as tune learning rates for the boosting models, see if decision tree could ever catch up to the top performers if we were to prune it extra, or just so many different things. But one thing we definitely learned from this project is that the tree-based models were very powerful right out of the box with very little data processing or parameter tuning for both classification and regression. And like Isaac said, we just want to put a disclaimer out there if you were ever to use these models that they're not perfect. 77% accuracy certainly isn't perfect. 40 RMSE is certainly not perfect. But we feel like this project and this class have taught us a lot about if we were to really spend time in a job every day, how we would go in and optimize each one of these and use them according to their strengths and weaknesses. And so this is our kind of our analysis and our modeling of the bike share data. And thank you so much.